Okay, we're now going to look at vertical SHM from a particle suspended on a string or a spring vertically. So if the particle's hanging in equilibrium attached to the end of a spring and it's displaced vertically, it will move with SHM, it will perform complete oscillations, and the centre of oscillation will be the equilibrium position. Quite an important point. For a particle in equilibrium attached to one end of an elastic string and displaced vertically from its equilibrium position, the particle will move with SHM if the string is taut and complete oscillations if the amplitude is no greater than the equilibrium extension. But if the amplitude is greater than the extension, the particle will move freely, so it will just move under gravity while the string is slack. So essentially, if the string goes slack, then you can use Suvat equations. Okay, those points are pretty important, and that forms the basis of everything that we're going to do. So we'll now move on to a example question. It's question 1. So for your reference, the question is here. So it's a particle of mass 0.75 kilograms hanging at the end of a light elastic spring. Modulus of elasticity given, natural length given. So calculate the length of the spring. So the length of the spring is obviously the natural length plus the extension. Okay, so just applying tension is equal to the weight, running the tension through here, we can find the extension's 0.1378 meters, and therefore the total length is 1.5. Let's just change that to a big L. 1.5 plus this 0.1378, and the units there obviously meters. So part B, show that the P moves with simple harmonic motion, and that hasn't changed since the previous section of the course, which was looking. So yeah, as I was saying, it was no different to proving that something moves with simple harmonic motion whether it's on the flat. All you have to do is show that the acceleration is proportional to the displacement but in the opposite direction. So if you start off with the two forces, you've got the weight downwards and you've got tension upwards, and that equals the mass times by the acceleration. You're just saying they're going in opposite directions to show the tension is always upwards. You may be wondering what happens if it's under compression. Well, it's simply that the tension would switch sign, and then yes, you could get a positive. So anyway, the tension, formula for tension is given here. So we insert our value for lambda, we insert a value for the original length, and we have the extension. Okay, here's the extension plus E. Okay, so the extension is X. The original extension of the original spring to give the point of displacement is just given as E. And because we have a formula for E, we can put that in to the equation. Okay. So carrying on, we have some things that will cancel, and so we're left with this down here. So to just go through those steps, this 0.75 G, if we look up, 0.75 G was the tension, which was in terms of E earlier. So this is in terms of E, this is in terms of X, this is in terms of E, and if you look at what cancels, these cancel, and it leaves you just with a term in X, which already is a good sign that it's going to be obeying simple harmonic motion. You've got this minus term in x is equal to, or is proportional to the acceleration. So when you get to here, you've shown that it's obeying simple harmonic motion because you've got acceleration proportional, here's the constant of proportionality, to displacement and in the opposite direction. So the next part of the question, part C, is to calculate the period of the oscillations. So the period we can calculate from omega, and omega is just given as this constant here, or omega squared is equal to this constant. So the period is 2 pi over omega, so 2 pi divided by the square root of this, or the inverse of this, is over omega. So we get 0.7450. Okay, so that's our final answer there. And last but not least, the final question was looking at the amplitude. So, the initial information given to us was in terms of v squared. So if I go back, we have the particle passes through its equilibrium position, i.e. x is equal to 0, with speed 2.5 meters per second. So using the formula v squared equals omega squared a squared minus x squared equals 0, a squared we calculated, omega squared, no, a squared we're looking to calculate, or a we're looking to calculate, omega squared we've got, v is given in the question. So it's simply a matter of plugging the numbers in and solving. Okay, rearranging, and then you find a as the root of this. Okay, so fairly simple. Give it a go, see what you think, and the next video will be a harder example. Good luck.